Hello, everybody. We are going to talk about data-oriented programming. My name is Yehonathan. I was born in France, near Germany. Right now I live in Israel. And actually I was in Berlin, first time in my life, 2 years ago to visit a customer. It was in Berlin. That's it. You can find me on Twitter with this Twitter handle, Ziebel. I've been a developer for almost 20 years now. I have an open source project called Clips. I'm the author of the book Data-Oriented Programming. You can see here the address of my blog. And currently I'm working here in Israel for a tech company, a cyber company. And our main technology is Clojure. So first I have a disclaimer. I'm going to tell you in 10 seconds about my knowledge in Go. So my knowledge in Go is very, 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 very limited. I know two things about Go. First of all, there is this thing that I like. It's a Go board. It's really a great game, but I don't think it has anything to do with the Go language. And second thing is I have a T-shirt with the gopher that a company sent me, Traffic Labs. And they sent me the T-shirt because I published, just a second, a blog post in my blog with a gopher, but not only a gopher, but with interactive evaluation of Go code snippets in the client side. So no server is involved. Hello, Go. And as I type, the code is immediately evaluated. Actually, it's not, I developed a plugin called Clips that makes it possible to evaluate JavaScript code in the browser. And someone ported the Go compiler from Traffic Labs into Clips and made this interaction possible. For some reason, they saw that I did a great job, so they sent me the T-shirt. And an hour ago, I looked at Go to see if there could be a connection between data-oriented programming and Go. And even if the answer would have been no, I think that it's anyway an interesting topic. But from what I saw in the way you can manage dynamic data in Go, I'm not sure if Go is a statically typed language or statically typed language with dynamism support, or you will tell me. But from what I saw, data-oriented programming could be easily implemented in Go. And as Arne mentioned before, the principles of data-oriented programming are language agnostic. So you could apply them almost in any language, but in some languages, it's more challenging, like in Java, for instance. In a language like Clojure is trivial. I think that in a language like Go, it's somewhere in the middle. And I think,
really... Go is a bit more Java-like in that regard.
Yes, but what I saw that there is a support for example, parsing JSON into a string map.
Yeah.
And there is something called type assertion, where you could say, I have something, I don't know what it is. If it's a string, do this. If it's a number, do that. In Java, it's much more difficult. You need to do static casting. And I think in Go, it's a bit more natural from what I read, but I might be wrong.
It's at least vastly shorter.
Okay, yeah, for sure.
There's a lot of type inference, and you have interfaces which are, in contrast to the ones in Java, implicit and not explicit. So you have a function with a certain signature, and then that interface applies. And for the other parts, there's also there's reflection used behind the scenes.
Yes, but from you as a programmer, you don't care, right? You don't have to explicitly do reflection. It feels like a natural code, right?
Depends. There's certain APIs where reflection is built in, for example, formatting a string and things like that. But and also this XML or JSON decoding, they also do that behind the scenes. When you call unmarshal, it just sees if the right function is available, if this interface exists. But if it doesn't, it uses reflection. Still, I think it's probably possible to create something for data-oriented programming with the right patterns.
Okay, so I'd be glad that you tell me when I expose the principles if how easy or how difficult it will be to implement in Go. In the presentation, I'm going to show kind of pseudocode, a bit of JavaScript, a bit of Java to illustrate the concept, but really feel free to tell me how it would feel in Go. So the purpose of data-oriented programming is to reduce complexity of information systems. So let's define complexity. In computing, we have two kinds of complexity. We have computational complexity, which is related to the amount of machine resources that it takes to run a program. And we have system complexity, which is the amount of brain resources it takes to understand a program. In the context of this talk, we are going to talk only about reducing system complexity. We are not going to deal with improving the performance of a program. So the goal is to make our programs simpler to understand. That's the goal. And also, we are going to narrow the scope a bit. We are not talking about building a program in general. We are talking about building an information system. What is an information system? It's a system or a program that manipulates information in various ways. For example, a web service that fetches data from a database and serves the data as JSON with a bit of manipulation, maybe. Or a web worker that processes JSON event, RPC event, and reads them and pass them forward. Or front-end application that runs the browser that needs to manage application state. What would be an example of something that is not an information system? It could be a compiler, it could be a game engine, a soccer game, a Go board game, stuff like that. So when you don't own the data, when the data comes from the outside, then this is what we call an information system. And what is important to notice is that when you are not the owner and the consumer and the producer of the data, you don't know exactly what kind of data you are going to deal with. You hope that you know the structure of the data, but sometimes you have surprises. And the claim is that the traditional way of programming, call it object-oriented programming, statically typed object-oriented programming, put too much of inflexibility on the program. And it's very hard to adapt to a dynamic world where data could be partial or missing or whatever. So data-oriented programming basically is about 4 principles that aim or are a consequence of treating data as a value. What do I mean by value? Think about, let's say, number in any programming language in 2020. Number is a value. And what is a value? A value never changes, right? If you have a variable A that holds the number 42, and you decide to increment the content of the variable, and you decide to add 2 to 42, 42 change. 42 is 42 forever. You cannot change 42. You can compute a different value and maybe assign this value in the variable, but the value on itself does not change. If you have another variable, let's say b, that points to the same value as a, when you increment, not point in terms of pointer, but hold the same value, when you increment one value, you don't influence the other value. So value are immutable. That's the definition of the value. And another thing that is a little bit more subtle is that there is no ceremony around creating a value. We have value literals. Usually we don't create a type for a number that is between 2 and 10. We have a number and maybe we assume that it is between 2 and 10. Maybe we check that the number is actually between 2 and 10. There is no ceremony. We are not going to statically declare that we expect our number to fit some criteria. So now we are talking about data, aggregated data. Think about records, arrays, collections, stuff like that. So what would it imply if we want to treat data as a value? First of all, it means that data lives on its own, separated from the code, not inside object, like usually we have in object-oriented programming. Number two is that we would prefer to represent data with generic data structures. Like I said before, we don't want to have too much of ceremony around representing data. We want to instantiate, to have at least the possibility to instantiate data as it is, like a number. I want to be free to say x equals 42. I don't want to say x as a number between 10 and 50 is 42. So the same is going to hold with data. Number three, we don't want to mutate data because we want to treat data as a value and values are immutable. And number four, when we want to check whether the data conforms what we think it should conform, we want to be free to create a data schema separately from the data representation and decide when we want to check whether the data complies with the data schema. And we are going to drill down into each of those principles. But before we do, please notice that all those principles are language agnostic. You could apply them in OOP or in functional programming. You could apply them in statically typed languages or in dynamically typed languages. And in a sense, we are not reinventing the wheel here. Each of these principles is kind of part of best practices that many programmers have adopted over since the beginning of programming. And you can find traces of those principles in almost every language. There are lots of books in Java that guide you to not mutate data. There are lots of books in Java again that says it's better if you can separate your business logic from your data representation, etc., etc. The idea of data-oriented programming is the combination of the four principles together. Okay. So before we understand how those principles reduce system complexity, let's think about what usually makes a software system
somehow your sound dropped out.
Oh, sorry, I pressed the mute button. Thank you. Please allow me to take as an example an online library management system. You know, you have a catalog, you have books, you have members, authors, librarians. We can borrow a book, we can check out a book, return a book, stuff like that. if you are a regular object-oriented programmer that is not aware of smart design patterns, you might come with a design and a class diagram like the one that you see on the slides. You would have a library class, a catalog class, a user class, a member class, a librarian class, and there will be relations between the class. For example, librarian inherits from member, librarian inherits from user, and librarian uses member. And in a library, you have multiple librarians. It's in composition, and between book and author, you have a many-to-many relationships, association, stuff like that. It's not a very difficult system, but quite rapidly the system, the class diagram is complex. Look at this. Look at this node, the librarian node. It is involved in 1, 2, 3, 4.
I'm sorry, I currently don't see a diagram. Are we supposed to see a diagram?
Oh, you don't see a diagram?
I see a slide, what makes a software system complex? And to the left, there's a row of, no, there it is.
Now I can see it.
Okay, sorry, I pressed, I know there is a pause sharing button that I pressed for no reason. Sorry about that. Mm-hmm. Okay, so, okay, take a few seconds to look at the diagram.
Mm-hmm.
Okay, so this, my claim is that this diagram is quite complex. And why is it complex? Remember, by complex, I mean how to understand, how to maintain, how to add features to a system like that. And the main reason is that there are many relationships between the entities. And also, not only we have many relationships, we have many kinds of relationships. We have association, composition, inheritance, usage, and it's a burden on our mind to keep this information when we develop the system and when we want to refactor the system, when we want to improve the system, when we want to add new features to the system. So let's see how principle number 1 reduces the complexity of such a system. Principle number 1 says that we have to separate code from data. How it will look like? Data would be represented with either classes, but only with members, with no methods. In some languages, it could be records, immutable records, or it could be string maps, like in JavaScript with object literal. And for the code, we will have the code gathered either in classes, but with static method only, with no state, or with stateless functions that receive the data they manipulate as an explicit argument. So no state and no encapsulation of data inside objects. Let's see how it looks like more in details for data. So depending on the programming language or your personal taste, you could have one of the three. Let's say you want to represent a book, and a book in this simplistic scenario is made of 2 fields, a title, which is a string, and a publication year, which is an integer. So you could have a class book with only members with title and publication year. That's one option. You could have record. That's in Java, I don't remember, 16 or 14, they have added support for record, which is almost the same as a class with members only, but it adds lots of nice features for free, like copy constructor and hash code and stuff like that, and it's immutable. Or you could have string maps, like JavaScript literals. So please tell me, how would you represent data, this kind of data in Go? What
usually a struct, which would be like record.
Okay. And are structs immutable in Go, or or mutable?
No, they are not. But you could
Not what?
just
Not
refrain
or,
from.
not immutable or not mutable?
They are not immutable. They are mutable.
Okay.
So what you can do is having the fields unexported, which means it's private. Yeah. And or package private. In Go you only have package private and public, and that depends on how the name is pronounced. If it starts with a capital letter, then it will be public. Otherwise, it will be package private.
And then you will have a setter and a getter.
You usually wouldn't grant access to that thing. So in Go, you don't use setters and getters at all. I mean, you could, of course, but you usually don't. And the code is quite clear and not overly complex, but that's more conventions. But you could definitely make sure of not changing the code in your package and having the variables in the struct package private, and then granting access based on certain methods you add. That but usually those wouldn't be getters and setters, but things that really do something that makes sense.
Business logic.
Yeah.
Kind of. Okay, so let's move on to the business logic part, and you tell me.
Oh, and one more thing that's a bit interesting and different in Go is you don't have something like class, which wraps all the methods inside, but you have the struct, and all the methods can be in different files in the same package.
Okay, nice. Okay.
Exactly. That allow you to have to separate the behavior of your code in many files in your domain, or you.
Yes. Definitely. It sounds very valuable.
And you can also do code generation without a lot of issues, because you can add something like a validate function, and you use static code analysis to read in what this struct looks like. And there's a library support in the standard library to do these things. So you can just go over your code and add validation functions based on struct tags or comments or whatever you want. Certain things you shouldn't really do, but really all is possible. And then you could just generate them as files next to the ones in your package, and they would be compiled with that stuff, and those functions would be available.
Okay, nice. Someone else would like to add something? Okay, so let's move on.
Sorry. One more thing. Classic Apple. You have for the types, you have slices, or I mean arrays and slices. You can think of a slice like an array list or something, and maps, and those are primitive types. You don't have a lot of additional collection things. So the number of data types you use to construct your own types from is not overly complex, not like the Java collection library.
Like it's like JSON, you have arrays and maps, or you have.
Yeah, exactly. And you have great support to manipulate those with built-in functionality.
Okay. So in terms of code, I can see two options: either classes with static methods, or stateless functions maybe gathered in packages or modules or namespaces. And it would look something like that. What's important is that no matter what is the approach, the data is passed as an explicit argument and not as an implicit this variable.
Yeah.
So I guess that's how we usually code in Go, right?
Yep.
We separate. Is there a possibility in Go to have stateful classes, or it's not supported?
In Go, do not exist static methods with class. Are functions.
Functions, okay.
You just have functions, and you can have a callee type, like the thing you can call this on, and that is like using the thing you called it on as the first argument.
Mm-hmm. Okay.
So you can have regular functions not associated with anything, just pure functions. That would be like static functions in a class in Java, and the others would have a would be called on something, and that is like having a regular function where that is the first argument, but it's a bit of magic rewriting and so on.
But
So
is
like
there a concept of a method that changes the state of an object?
Exactly.
There is, or there is no? There is not.
You have the choice. So
You have the
as your
choice.
first implicit argument, you can either decide for passing in values or requesting a pointer to that type thing. So if you go for the pointer, you would more lean in the stateful area.
Yeah, and
so
one thing that's also different, you can call stuff on nil, I mean, which would be null in Java, and that does not throw any kind of null pointer exception or something like that. It's just you can check in the function what the value was that that function was called on.
Yes, so that's also useful.
And multiple return values, but that's independent of that. That's also very nice.
So if I were to summarize in terms of Go, the principle number one, it would be avoid stateful classes. That's it.
Yeah.
And it could seem trivial, but if you look at the impact it has on the simplicity of a UML diagram, the moment you take each stateful class and separate it into two classes, one for the code and one for the data, like for example, the library, on the left, we have library code, and on the right, we have library data, then suddenly, magically, instead of one big entangled diagram, you have two simpler diagrams. And then you have less relationships between the nodes. And for human beings, it's simpler to understand two simple things than one complex thing. So that's the importance of the separation between code and data. But it sounds like you are already convinced. So let me try to challenge you with a less obvious principle. Represent data with generic data structure. That might be the most controversial principle. So first of all, a bit of terminology. When I say a record, I mean something that has fields into it. And record, no matter what is the programming language, it's a programming concept, or even it's a database concept. For example, you could say in a database, each row represents a record. Now, the question comes, how do you represent a record inside your program? And you could represent a record with a data class, or you could represent a record with or a struct, or you could represent a record with an heterogeneous string map. And that's what data-oriented programming advises. So instead of having a struct that defines what is a book, you simply create a book with the fields. Here in JavaScript, you pass to the map constructor an array of pairs. So the first pair is made of the field name title and the value is watchman. And the second pair is the field is named publication year and the value is 1986. And that's it. No ceremony. No, even at this point, no type inference. But for sure, at this point, no explicit typing. And in some languages, you have even support for map literals. So it looks a bit shorter. But conceptually, it's the same. before you tell me if you agree or disagree, I think that in Go, it might feel a bit awkward to represent a record in one or the other. You'd prefer to have a struct, right?
Yeah.
Okay. So before we debate,
you could have a map string to interface, which is basically mapping a string to any value.
I know you could.
But then it's not type checked, which is kind of a strong suit in Go.
Yeah. So you could, but probably you won't, right?
Right. The first tendency would be to use structs.
Okay.
It might be beneficial in certain scenarios to do a map from something to whatever, but just if you want to be able to iterate over the keys in a generic way without using reflection.
Yes. So let me think about this scenario. Let's say you have a web service that fetches data from a database.
Yeah.
Let's say books, a collection of books, and returns a JSON representation of the books.
Mm-hmm.
And I'm adding another requirement. This web service is over HTTP, and the HTTP endpoint receives also the names of the fields that it has to return. So let's say a book has 10 fields. The user can send, I don't know, only 3 fields that he wants to retrieve.
So like a GraphQL.
Like a GraphQL. And let's say that for the sake of the exercise, that you don't want to do a projection on the database, that on the database, you can only fetch all the data. Let's say it's not a database, it's an external API that doesn't support projection. So you need to fetch data from this API with all the fields. And then in your code, you need to project and remove or keep only the fields that the user asks you to keep. How would you do that if you represent a book with a struct?
Well, I think it mostly depends on if the data source is schemaless or if you have a schema. Because if you have a schema, then you have a lot of value by using those types. And what you would do is creating the query or the request to the database in a way that just those fields are returned, and then then they will be assigned to the fields in the struct, and you'd use the struct. But if you have schemaless data you don't know before, then you'd definitely strive to take a dynamic solution where you would use the map approach.
Okay. So exactly. So in those, so that's the kind of scenario I'm talking about, with lots of dynamism, and the value of having a struct is not high because you are just like a pipe. You receive data and you pass it around. You are not going to do calculation with the publication year. So in a sense, you don't care if the publication year is a number or a string. And if for some reason in the data source, the publication year is for one record is kept as a string, you don't care. You pass it back to the client and the client will deal with it. And that's maybe a mind shift that would be required, but I hope you start to feel that it brings lots of flexibility to our system, the ability to be able to pass data around with no need to check and make sure at any second that data is exactly like I think it should be.
That's definitely something you'd use in schemaless or previously unknown data, where you say you write a program that should run somewhere for any kind of database which you don't know beforehand, where the schema is unknown. If the schema is known, you'd usually probably still pick the struct, but that probably also depends a bit on the stuff you'll tell us about later.
Yes. Okay. So now, instead of a diagram like this, with two simple diagrams, we have only one simple class diagram, because all the data hierarchy is not present in our program. It's present in our head, but not in our program. And this is what I call a weak dependency between code and data. So the code knows the kind of data it manipulates, but it knows it implicitly. It doesn't know, it doesn't have to know a priori. You are able to manipulate data without having to import the type definition of the data. So in a sense, it creates a loose coupling between the components in our system. It's less of a rigid coupling. And the data model could be flexible in the sense that you are allowed to add new fields and remove fields on the fly, without changing your code. If for some reason the user asks for, let's say that your data sort has a new field that you didn't anticipate. In the book now there is ISBN 13 and you didn't anticipate. If you code with structs, with static typing, you have to deploy a new version of the program that supports this field. If you code with generic data structure, you don't care. The user passes you the new field, you pass it to the external data source for the query, and when you have the response, you pass it forward to the client.
Got one question. How would you make sure that that the user doesn't misspell the fields, like capitalization and things like that? So would you just not return that field that was misspelled, or would you still return an error because you can't find it? And would you use things like lower casing and so on, or would you avoid that?
Okay, great question. I'm going to answer when we talk about data validation, principle number 4. But that's a great question. Last benefit I'd like to mention is that when you represent your data with generic data structures, basically arrays and maps, you have a plethora of data manipulation functions that are available for you for free. Sort by, group by, projection, reduce, flat map, all the. Do you guys remember when C# came up with LINQ?
Yeah.
It was a big deal, right? It was really a big deal. They invented Lambda and they were able to do reflection and you could manipulate data from in memory, in SQL. Really, it was a piece of magic. But when you represent data with generic data structure, it's trivial to implement a library like LINQ. And in fact, we have, like in JavaScript, we have libraries like Lodash that provide dozens of data manipulation functions, and nothing is magic there. It's simple to access fields, to create new versions of data, new fields, to declare, to know or to support fields that are optional or nullable. Everything works in a simple manner. Of course, there is a trade-off between flexibility and security or stability, but I think we should allow ourselves to move the blob, or not the blob, the knob a bit more toward flexibility. And as I told to Arne, I'll mention later how to deal with data validation. Other questions? Okay. So now it's time to take a meditation posture and simply breathe. Breathe and feel how simple could be our life if we remove all the layers of abstractions that are projected by our minds on the reality. All the concepts, all the judgments, all the things we think about why this guy said this, why this guy said that, why it always happens to me, all the burden in our mind, all the thoughts that in meditation we try to liberate ourselves from. And it's challenging, it's difficult, it's takes us out of our comfort zone. But when we are able to do that, we are free, we feel great. So in a sense, data-oriented programming is like meditation. It encourages us to remove layers of abstraction and to be in direct contact with reality. And what is reality for a program? It's data. So the less layer of abstraction we have between our code and data, the happier we are. And another benefit when data is represented as data is that we can do cool stuff for free. For example, we can visualize our whole system data in the console. We can store the system data on a file in JSON, for example. We have serialization for free. I know that in Go, you have serialization even when you use tracks, but in many languages, like in Java, supporting JSON serialization for data classes is a nightmare. And also something nice, each piece of data in the program has kind of an address, what I call here the information path. It's an array of all the nodes that you have to go through in order to get data. And I think it's cool that any piece of information could be referenced by its, like the address, the information path. I'm going to go quickly on this one. So not mutating data, I think it's a common agreement that it's beneficial. The question is how to do that in an efficient manner. So one way to, okay, we need to change data. We have, let's say, a checkout cart of a customer that starts empty, and now the customer adds a new item on the cart. When we say not mutating data, it doesn't mean that the cart will be empty forever, right? We want our state to evolve. But what we want to avoid is changing in place the value of the object that represents the cart. Think about Git. We want to commit new version of our code, but we don't want to override older version. And the way to do that in programming is called structural sharing. And how it works is that, for example, let's say you have the current version of the library where in the book Watchmen, the publication year is 1987. And now you want to create a new version of the library when the publication year of Watchmen is 1986. One way to do that is to do a deep clone and to change in place in the new version of data, but it's not efficient. A much more efficient way is to create a new node, that's the pink node here, the library, and to copy only the changes. So, for example, the user management field inside the library is the same between the previous version of the library and the next version of the library. So we can share it. We need to change only the catalog. But in the catalog, the authors by ID is the same. We can share it. So we need to create only a new version of books by SBN. And in books by SBN, you have thousands of books, but we need to change only Watchmen. So we will copy all the references to the books and only create a new node for Watchmen. And in Watchmen, all the fields are the same. We need only to create a new version for the field that we want to change. And this is what we call structural sharing, and it makes creating new version of data very, very efficient with no copy and write, with no deep cloning and nothing. And it's a bit like Git works with trees and nodes. Trees that are not changed are shared by reference. And only the trees where there is a change in one of the nodes, a new tree is created. So Git also leverages structural sharing. In practice, there is support for, there are two ways to do immutability. One way is with native data structures and having special functions that manipulate native data structures, like in functional Lodash or in Ramda or in Immer. And even there is a proposal for ECMAScript to support what they call record and tuple, which is record is immutable maps and tuple, they mean immutable vectors. And in Java, since Java 14, there is support for immutable records. There is another way to achieve the same, even a bit better, is leveraging special data structures, non-native data structures, what we call persistent data structures. But then you need a third-party library to implement that. And there are libraries for it in almost every language. In C# and Clojure, that's the native, sorry, in Clojure, the only data structures are the persistent one, the immutable one. In C# you have both. C# supports natively immutable data structures. For most other languages, like Go, you need a special library. There is a library that I found this morning called PEDS that supports persistent data structures. Okay. Now to the last piece of our presentation. What about data validation? Like Arne asked before, what happens if the user mistypes a field? For example, let's say I have a book, and instead of the field name title, someone mistyped and typed the title. What will happen with the approach I have presented so far? With the approach I have presented so far, bad things will happen. If you call the function bookinfo with an invalid book, you will have a very weird behavior. Instead of Watchmen was published in 1986, you will see something like that. Was published in 1986. In some cases, you might have done the stack, a very weird exception will be thrown. Sometimes it will misbehave and you will not know where does it come from. And it could be a nightmare. But there is a solution to this problem. And the solution is to leverage a schema language. For example, JSON schema. So you are free to instantiate data as you want with generic data structures. In addition to that, in your program somewhere, you write your schema for your types. For example, here is the information for the book schema. It's an object. Two fields are required, title and publication year. Title must be a string and publication year must be an integer. That schema that is stored somewhere, for example, in a JSON file. Now I can bring a JSON schema validator library, for example, AGV in JavaScript, and I'm instantiating an instance of AGV. I'm passing the schema into a data structure. So I have now a book schema at runtime. And in my code, in book info, first thing I'm doing is to validate that the book I received is conformed to the book schema. And if it's not conformed to the book schema, I'm going to throw an exception with the information about why it doesn't conform to the schema. This library AGV is smart enough to not only say it's valid or not valid, but to give you information about all the reasons why validity didn't pass. And that's an information that you could send back to your user. So if the user mistype a field, you won't send him back error 500. You will send back a bad request. And in the body of the response, you will say, this field is missing, this field is missing. this field must be a number, and you passed a string, etc., etc., etc. And this resembles a bit what we are used to with static typing. So now if you call again book info with an invalid book, that's the exception that will be thrown. Data should have required property title, or book info called with invalid argument. Does that answer your questions, Arne?
Yes. I have the suspicion that for picking Go as a language, you usually don't have these dynamic scenarios, but more performance-oriented ones. And in these cases, that would probably be detrimental because you have a lot of string comparisons. But it's definitely applicable for some situations. And in those situations where it applies, especially for validation, we have the wonderful luck that, in my opinion, one of the strongest schema languages that is available is written in Go, and that is Q, C-U-E.
C-U-E?
C-U-E, qlang.org. It's written in Go, has great support. It's amazing. It's very compact concerning the things you can express with it. It's up and coming. It's not not a 1.0 release yet, but it's amazing.
Does it run at compile time or at runtime?
At runtime.
At runtime.
Yeah.
Amazing. So, because one thing I'd like to mention.
So you could try. You could try to embed that, and with that you have a great validation functionality if you use those generic data structures. It can also ingest YAML and JSON, and you can convert between that and OpenAPI.
Yeah, amazing. Because in JSON schema, what you can do is you can say, okay, publication year is not only an integer, but it's an integer between 1900 and today, because it makes no sense to have a book that is published in the future. And because it runs at runtime, it's not a problem. So could you do similar things with Q?
Yes, even more. You could, if you go to that website, you can go to, sorry, I'm doing this on my smartphone, so it's a bit, if you go to use cases, no, sorry, you're on the right section. Just go to OpenAPI. It's a bit further down. OpenAPI and CRDs. And there it has. It should have a comparison between. I mean, there is one somewhere.
An example of
probably use cases validation. Then. For JSON and Q, this is also fine. It just shows you can. I mean, it's a JSON superset, the language itself, but the runtime is written in Go. And
so what? When you use that, how do you represent your data? With structs or with string maps or what?
It's just JSON. So no, it's totally flexible. It's like
so it's a new data type.
It's like it's an evaluation system written in Go that is its own language, and it's especially made for configuration. And its special property is that types are also values, and you can also have constraints. So you could say field A is a value larger than 5, smaller than 7. And you could also say field A is 6, and that would be valid. But if you would say field A is 8, then it is invalid, and it would tell you. And you can pretty much overlay all these requirements you have for your data.
But then let's say the data is valid. Then what? How do you represent the data?
It has its internal implementation that's just called value, I think. I didn't try to embed it yet, but I will.
Okay, keep me updated. I'm really excited by that. Really, really excited.
No, that's just a super cool project that's written in Go, and I can really just advise anyone to have a deeper look at that. But
I will definitely take a look. Okay, before we wrap up, just let me give you a brief overview of where does data programming come from in terms of the history. So it has its roots in functional programming back into 1936, where Alonzo Church discovers lambda calculus. It was then a mathematical concept, not really a programming language. But in 1958, John McCarthy, in a sense, implemented lambda calculus with Lisp, where functions were first-class citizens. In 1981, this guy, Brooke McLennan, wrote a beautiful and simple to read paper. I really encourage you to read this paper. If you need to take one thing from this presentation, is an advice to read this paper, Values and Objects in Programming Languages. What do we mean by a value? What do we mean by an object? Why it is difficult to share objects? Why is it safe to share values? Why mathematics is simpler than programming? It's 5 to 7 pages, really simple and really, really deep. But until the year 2000, it was not really possible to have efficient persistent data structure. And I think that's why data-oriented programming was not well known, because in Lisp, the way you manage immutability was to copy every time you need a small change on your data, you had to copy, and it was not performant. But today, on the first thing, our computers run much faster. And secondly, we have smarter algorithms to deal with immutable data. And it started in 2000 with Phil Bagwell inventing ideal hash trees. And Rich Hickey implemented ideal hash trees in 2007 as the underlying data structure for maps and vectors enclosures. And in 2021, I hope to release my book about data-oriented programming. So one picture was 1,000 words. You can look at the mind map on the left. When we want to write a system, an information system according to data-oriented programming principles, we separate between code and data. The code could be either in a FP flavor or OP, doesn't matter. The data should be represented as generic and immutable data structures, and the schema should be kept separate from data. And when you do that, hopefully you benefit from a flexible and simple system. If you like this stuff or you want to go deeper, I encourage you to take a look at the book, Data-Oriented Programming. And if you agree or disagree with me or want to share your thoughts, you can send me an email or write on Twitter. Or another thing that would be very, very cool, I'm going to share a link to, I made a couple of challenges, and I encourage folks from different programming languages to implement small exercise or small programming puzzles in their preferred language. And people wrote, I'm not sure if someone already came up with implementation in Go, but it would be interesting, Arne, if you could provide an implementation with Q to this kind of challenges.
Maybe.
I think that's all what I had for tonight.
Great, thank you so much. So this is super, super interesting. And I think it's, of course, always super important to track what's happening and have a look over the fence and not stay in your own language. And getting to know other things, concepts, and so on is it's amazing. And I think this is a very, very nice way to deal with the a very dynamic, previously unknown environment. If you run your programs in a situation where you don't have a schema that's known beforehand and that is really for everything, or if you want like this tree visiting functionality and displaying all kinds of things. So yeah, just thank you. It was great.
Thank you, and I'm really curious to learn more from the Go community how to solve this kind of schemaless situation, and how to leverage structs or marshalling or string maps, or how to make an orchestra from all these programming constructs.